Okay, in these few videos I will show you some interesting things about sequence and series, in particular series. Chapter 11 of Stewart's calculus textbook is dedicated to sequence and series, and we are interested in series. So it turns out that except for two types of series, geometric series, and telescoping series, mostly other series, we do not have a concrete way of finding the exact value of the sum. If you're just given a random series like this, n from 1 to infinity, we don't know how to compute this. But when it's geometric, we know how to do that. When it's telescoping, we know how to do that. For other cases, what people do is that they approximate the series. Let's just use k for now. Let's say k runs from 1 to infinity, k. So what people do is that they approximate this series like this and say, okay, let's just let k run from 1 to n, where n is a number as large as possible. Okay, so since this is what is obtainable for most other series, we should find a way to be able to tell how much good we are doing in this approximation. We should have a way to quantify how good we are doing in this approximation. For instance, if n is 100, then this series is like summing from 1 to 100 ak. Now, how close is this number to exact value of the series? We don't know. So what people do is they say, okay, let's define a quantity Rn and call it the difference between the exact value of the series and our approximate value. The difference between the exact value of the series and our approximate value. So people start thinking, how can we quantify this Rn? How can we quantify Rn? How can we quantify Rn? How to quantify Rn? It turns out that it's not easy, because to find Rn, you actually need to know the exact value of the series. And if you knew the exact value of the series, then there's no point approximating the series. So what people have done is that, okay, since we don't know exact value of this, can we find something, a bound, just a bound, something we can tell that, oh, this is how good we are doing, but we don't know exactly, but given this approximation, we are as good as this. So finding that bound is what I'm about to show you how to do in these short videos. It turns out that for series that satisfy the properties of what? Integral test. So suppose we are interested in approximating the series ak, k from 1 to infinity, and then what we do is we call this ak, let me use k, so call this a function ak, and then we need to check few things. Call this x, and for integral test we need to check that f is what? Positive. F is what? F is continuous. F is continuous. And then finally, F is decreasing. Okay? For any series such that the nth term, which is ak, we rewrite it as a function of x, satisfy these three conditions. In particular, this condition should be satisfied on the domain of the series. For this particular case, the domain is 1 to infinity. So for any series that satisfies these three conditions, then integral test applies, right? So I'm not going to bore you with things about integral test, but let's see how we can characterize this Rn, find a bound for this Rn. Let's see. So the first thing I'll do is to use the decreasing property of the sequence of the series, which is ak, or f of this. So let's see. So ak, this f is decreasing, means that ak is also decreasing. So ak decreasing means that ak plus 1 is less or equal to ak. So this is decreasing, and in particular the property we are using is non-increasing because we have equality involved. Okay, so from this happens for any k in this domain. Now let's sneak in f of x in between this, because f of x is actually continuous, right? Which means there's a lot of values between k and k plus 1. So we can sneak in f of x in between, and this is for all x in what? k plus 1. Notice that we can do this since f is continuous and f is also decreasing, which means this should be true. Okay, so since we have this, we can now integrate. Since this is continuous, we can integrate from k to k plus 1 dx. Integrate from k to k plus 1 dx. Integrate from k to k plus 1 dx. Or I have a number, so this is ak dx, and this is a constant, and this is a constant. The only thing that depends on x is this f. So let's see. This now gives us integral of this is ak, it's just a constant, x. Then we evaluate from k to k plus 1. This one remains the same, k to k plus 1, f of x dx. Then this one is ak, x, and we have to evaluate from k to k plus 1. Okay, so if you plug these values, you have ak into k plus 1, this is k plus 1, minus k, the upper one minus the lower, then this holds, k to k plus 1, f of x. We don't know this, so we leave it alone. And then this is less or equal to ak into k plus 1 minus k, right? Okay, so work this out, you actually get 1. So it turns out that this just leaves us ak plus 1, and then we have integral from k to k plus 1, f of x dk. This is less or equal to what? ak. And this thing holds for all k in the domain we are interested in, right? Notice I have not assumed anything about k. Okay, now this is where things get more interesting. This is k, please, not x. This is k. This is where things get more interesting. So since this is true for all k bigger than or equal to 1, what happens when k is 1? What happens when k is 1? So when k is 1, you plug 1 here, you get a2. You plug 1 here, you get integral from 1. This one becomes 2. Then f of x dx. Then this is a1. When k is 2, you plug 2 here, you get a3. and then this one is a2, this is 3 f of x dx. This will be less or equal to a2. And when k is 3, if you put 3 here, you get a4 is less or equal to integral from 3 to 4 f of x dx is less or equal to a3. Okay, and clearly you can see a pattern that if you continue this, you get to, let's say, ak. Okay, let's not say ak. Let's assume k is the one running here. So we'll get to a point an such that notice that what is here is 1 bigger than what is here. So I'll subtract 1 from this, and then what is here is exactly what is here. So this is n, and then f of x dx, and this is less or equal to an minus 1. Interesting. Okay, so you can't stop me from taking a sum of this and taking a sum of this and taking a sum of this, and these inequalities will still be satisfied, right? Okay, so if you sum this one, then k will run from what? 2 to n, and then ak. And if you sum this, you have integral from 1 to 2 plus integral from 2 to 3, from integral from 3 to 4, like that, plus 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 plus, and it's the same thing. It's nothing but integral from 1 to n, right? F of x dx, and this is less or equal to, if you sum this, you have sum k is running from 1 to n minus 1 ak. Let me write this well. So this is ak. This is interesting. Now notice the pattern we have here, that this sum start from 2 to n, the integral start from 1 to n, and this sum start from 1 to n minus 1. So let's call this maybe question 1, and we'll see how this is useful in subsequent videos to estimate this Rn, to just tell us how good we are doing in our approximation of this infinite sum by a finite sum.